So this one, again, starts out in the same way as all these problems do. Find the volume of the solid obtained by rotating. In this case, it's the area between y equals x plus 3 and y equals x squared minus 2x plus 3. We're going to rotate that about the x-axis. Okay. So here, in doing things like this, sometimes knowing how to find the area between the curves can be handy. That makes you like practice graphing these and stuff. So again, another plug for the 5.6 area videos. You could use some of the ideas there to find the intersections of those two curves by setting the two functions equal to each other. Okay, we could see we could get rid of the 3's there. Subtract the x squared minus 3x equals 0. Okay, so these curves are going to intersect where x equals 0 and x equals 3. That's kind of a nice thing to know for making our graph here. So x equals 0, x equals 3. Those are the intersection points. Okay, and yeah, that's going to help us make our graph here. All right. So, just making all my little tick marks there. There's 3. All right, so our first curve is y equals x plus 3. Okay, that's a line. Intercept of 3, slope of 1. Yep. All right. There's our first curve. And then our second curve here is the parabola. Y equals x squared minus 2x plus 3. That also has a y-intercept of 3. So they're going to intersect at that point right there. And then we have our vertex here. And that parabola ends up looking something like this. You only would have to plug in x values from 0 to 3 to get that portion of the parabola. All right. So yeah, we are going to take the area that's trapped between those two curves. That would be this portion right here. And we're going to rotate that about the x-axis. So rotating like this. All right, imagine the same type of thing. That portion of area comes out of the computer screen. It's going to rotate around until it hits back into your screen. It would make kind of a little shadow image down here. Okay, that's where it would be hitting the screen like that, and then it would continue behind the screen and make the full circle. So I'll try and sketch this solid for you as well. These get even weirder and weirder looking. What do you guys think this one's going to look like? Can you picture this one?
Will it look like a donut?
Yeah, it looks kind of like a donut with these weird straight sides to it. Yeah, but it's got that big hole cut out of the middle. So yeah, on the outside, we've got our straight line like this. But then, yeah, there's a hole and it makes kind of a donut shape. That's good, Natalie. Good visualizing. And I know you're into the food sciences, so donut is a good thing to think about. Although I don't know if they would ever have you calculate the volume of a donut in food science. So Yeah. Let me try and make that donut look a little better. Okay, so that's kind of what the outside would look like. And yeah, I agree with Felipe. It's more old-fashioned type of donut. Um, it would have, though, these weird, like even weirder than an old-fashioned. It would have these weird kind of bulges inside of it, like this, like these parabolic insides where the actual donut portion is. So here's donut, and here's donut, and then the rest of that cutout is like a really weird shaped donut hole. Yeah. But the fact that this is, you know, round and has a hole in it and kind of makes a donut type shape, that's what we're looking to think about there. All right. And yeah, straight down the middle of this donut, that's where our x-axis would be coming through. Let's graph this one on the website as well, just so we can really see our donut in action. All right. So yeah, let's take our two functions here, y equals x, and then plus 3. And then our second function, we have lowercase x squared minus 2x, and then plus 3. And yeah, let's see where we want our x values to go. Actually, we had a pretty nice idea of that on the graph and on these intersections here. Notice that our intersections are at 0 and 3, right here and right here. That's exactly the range of x values that we're going to want to cover to make this donut. So that's where we need to set our graph here. So x equals 0 to 3. Set your functions. And yeah, we can see our little area that was graphed. Let me tinker with the window there a little bit. X max, yeah, I'll set that to 4 just so we can see the full thing. Make the tick marks each be worth 1. I'm going to go from a little further out here on the y's so that we can fit that whole thing on the graph. Maybe -7 to +7. All right, so I'm going to set that. Yeah, now we can see the whole thing. Yeah, and again, we're going to want to revolve this about the x-axis. So cross y equals 0, and yeah, hit revolve. Boom. There's our revolution. So it's about halfway through now, hitting the screen and coming around to complete the full revolution. All right. And notice that it does compute our volume to 3 decimal places down there. So we can check our answer at the end. Oh, and question in the chat there, can this work for a 3D printer? Well, yeah, I don't know if this website in particular would communicate with the 3D printer, but this is the idea of a lot of 3D printing type of things. You can make these shapes. And actually, I wish we were in person because I asked our engineering lab to 3D print me a few of these, and this is actually one of the solids that they printed for me. So if we were in class, I would be able to like pass this around like an actual plastic one of these donuts for you guys to hold and touch and look at. But alas, we're not in person, so we can just look at a simulation of it. But yeah, these are great for 3D printing. All right, so here, virtually at least, we can look at our solid and we'll see the hole that goes through the middle of it. making our donut shape. Okay. And then, yeah, looking through this side, you can see the donut shape. The solidness of this looks a little better, I think, than the first one did. You can see that it is actually solid, but that also makes it so you can't see the parabola as well. Let's see. Reset the view. Let me see what the wireframe looks like. Yeah, there you can see the parabolic inside portion a little nicer. So that parabolic portion and this part down here, those are the actual solid bits where the dough of the donut is. And then the rest is the hole that's cut out. So all of this in the middle here is the hole. A wormhole. Interesting. Yeah. Maybe so. So yeah, there's our donut wormhole fabulous objects. Cool. I just think these are really fun to play around with. All right. So yeah, now that we can picture what it looks like, let's go compute its volume for ourselves. All right. So there's our sketch of this. Not too shabby, if I do say so myself. And now we have to think about slicing this object. So which direction do you guys think I should slice this? Should I take my knife and go vertically like this? Or should I take my knife and cut our donut like this? So vertical slice or horizontal? Got one vote in there, yeah, for vertically. And just to spoil it, yes, Brandon, you are totally correct. We do want to slice this vertically, because notice if I had sliced this horizontally, in some places, my slice wouldn't actually even have anything to it, really. If I made a horizontal slice right in the middle of the hole right there, well, there's nothing there. So that horizontal slice wouldn't really have anything to it. There might be some weird, like awkwardly shaped chunks on the sides, but it would not be a great idea. So we are definitely going to slice this vertically like so, so that we actually hit our solid. Okay, so just to show that on the graph here, looks like that. All right, and let's take out that slice. Now notice this one is different from our previous two problems because it is a donut with a hole in the middle. And so this is not a solid disc anymore. This is what we call the washer method, something that has a hole in it. So our slice is going to look like this with a hole rather than the solid disc. Okay. So one slice here is a washer. It has a hole. So we'll sketch that washer. All right, it's got a little thickness that way, and it does have a hole in the middle. Key feature there. Okay, I'll try and represent that hole. Okay, so we need to think of the volume of that washer. Okay. Volume of washer. All right, well, notice here that we're not just dealing with a single radius anymore. From our center point, we actually have a smaller inner radius right here, the radius of the cutout, the hole itself. Since that one's littler, we'll call it little r. Inner radius, little r. And then we'll have a radius that goes all the way to the outside of the solid. That'll be our outer radius. And since it's bigger, we'll call it big R. All right, and then we'll still say that the thickness of the shape, we'll call that acre height. Okay. So when we do our little change in volume, we can take the volume of the whole bigger outer shape and then subtract out the area of our hole that we cut out of the middle. So we could take pi big R squared h. That would be the big cylinder outside. So larger solid shape. And then subtract the cutout, the hole, pi little r squared h. So this is the cutout or the hole. Yeah, big dish minus small dish if it looks like kind of a dish shape. Yeah, gotcha. All right. So yeah, that's our little change in volume there. And this can actually be simplified a little bit because you'll notice both of those terms have a pi and the same h in them. So we can actually factor those out. So delta v, you can say, is pi times big R squared minus little r squared times h. Yeah, if you distribute that all back out again, you'd get the same terms, but just easier to think about there. Okay. So let's think about what we've got here. Here. What is our big outer radius? Is that given by the line or the parabola?
From the parabola?
So this one right here?
Well, I was looking at the top of it, but
Looking at the top of it. This part?
I guess the highest it goes, which looks kind of like 6.
Oh, yeah. So that is the biggest radius that we have. Yeah. The largest radius is going to be 6. That is the biggest outer radius. Yeah. I see what you mean now, Natalie. So yeah, for that outer radius, I can see what you're looking at. But we want to come up with like a general expression for like any slice rather than just the biggest overall, because that would be 6 at the base there. But if we're looking at the little like individual slice we took out, it's more like this type of measurement right here. So that would be big R, and then the cutouts radius would be that part right there, little r. Yeah. So yeah, for that bigger radius, you can see that we do need to go all the way from the x-axis out to the line portion. And that would give you that biggest radius of 6 at the end there. All right. It would also give you the right radius at any point in between. And yeah, Brandon's got our equation there. Our large radius big R, we are going to get from the line. And so yeah, we are going to use x plus 3 for that. For these, you might actually even want to decide on your h first, which we kind of did already. We just didn't state it necessarily. When we decided to cut this vertically rather than horizontally, we were saying that here h is going to be some change in the x direction. So that's what we're doing by setting it up that way. One little tip for these, by the way, if you're rotating about the x-axis, you should really end up using delta x and dx. So use delta x and integrate with a dx term. And then if you have a problem like the one we just did, if you're going about the y-axis, there you're going to end up using a delta y and integrating with dy. So your variable of integration should match your axis that you're rotating around for these type of problems. Okay, so yeah, here our h is delta x. So that I was just kind of confirming, that way we know that Brandon's got the right equation there. We do want everything to be in terms of x here. So we don't need to use like solve this equation to make it like the line y minus 3 or something weird like that. So we want everything in terms of x. And that's good. All right. Especially when it comes to our little radius, little r for the inside of this, little r comes out and touches the parabola. So there's our small radius, and the small radius changes depending on which x value you're at as well. So this highlighter is hard to use. So there's the little radius, and then unpredictable. All right, there would be our little radius, and then there. And actually at the very end of our shape, the small radius and large radius end up meeting up with each other, and both of them have a value of 6 because they come to that point at the very edge of the donut. But yeah, we're using the parabola value for that small inner radius to tell us where the hole is being cut out. So that's what we're looking at there. And so for little r, we are going to use the parabola's equation. So we'd put in, what was that? X squared minus 2x plus 3. Okay. And then, yeah, this does take a little bit more finagling here to simplify our little delta v expression. Delta v turns out to not be quite so little, because for a big R squared, we need to take x plus 3 and square it, and then subtract little r squared. So yeah, we're going to have to square out x squared minus 2x plus 3, and then times h, which is delta x. So a little bit gross there, but we can do it. All right. And I'd say the more you can simplify outside of your integral, probably the better, because then you don't have to keep writing the integral and the limits of integration and all that on here. So I'm going to simplify just in the delta v portion right now. So this would be x squared plus 6x plus 9. And then, yeah, squaring a trinomial like that kind of sucks. But you would literally just take off to the side here, x squared minus 2x plus 3 itself. And yeah, it does. It's not super fun. I don't know. What else can I say? So you go minus 2x cubed plus 3x squared, and then you do the same type of thing. Getting some common terms. Plus 4x squared, and then minus 6x. Good times, good times. We do it again. Okay, so you'd square it out like that, and then combine all the like terms. X to the fourth minus 4x cubed. 3 plus 4 plus 3 gives us 10. X squared minus 12x plus 9. Fun. All right, so that is what we're going to be subtracting here. The best. X to the fourth minus 4x cubed plus 10x squared minus 12x plus 9. Woo! All right. Super fun. Okay. And then you would distribute that negative and combine whatever like terms you have. So let's see. I'm going to go by powers of x here. And our largest one is x to the fourth. So we would have negative x to the fourth. And then for x cubes, we would have plus 4 of those. I'm distributing the negative as I go here. X squareds, we have 1 over here, and then we're going to subtract 10 more. So that'd be negative 9 x squared. For x's, we got 6 out here, and then minus negative 12. So 6 plus 12 would give us 18 x's. And then our constants, 9 minus 9. Hey, the constants go away. Small savings. All right. Delta x. Okay. So that's our delta v expression, as simplified as we can get it. So that's the thing that we're going to be integrating. And yeah, it does take a little doing to get to that point, but at least the integral is just going to be doing power rule in reverse. So at least there's nothing too nutso there. All right. Let's check out our limits of integration here as well. What are our limits on this? We do want x values, so x equals what to what? Yeah, Brandon's on it. X equals 0 to 3. So we're going from one intersection point to the other. So x equals 0 right here to x equals 3 right there. Okay, so yeah, let's set up our integral. X equals 0 to 3, and then you just pop that delta v expression right in here. Pi, I'm going to use parentheses there. Oops, negative x, not pi to the fourth. Negative x to the fourth plus 4x cubed minus 9x squared. Oops. Say one thing, write another. All right, minus 9x squared plus 18x. And then instead of delta x, you put dx. So that's what we are integrating. And the rest is integral fantasticness. You can pull your pi out there. Negative x to the fourth plus 4x cubed minus 9x squared plus 18x dx. And then you do your antiderivatives, which again is just a lot of power rule in reverse there. So we'd have negative 1/5 x to the fifth, and then just plus x to the fourth. That's cool. Minus 3x cubed, and then plus 9x squared. From 0 to 3. And so then you would plug in your limits, and you do some arithmetic, algebra, work with the fractions. Plugging in 0 wouldn't be too bad, but plugging in 3, you'd have to do a little nonsense with like 3 to the 5th and stuff like that. So I'll trust that you guys can arithmetic. The answer you'll end up getting is 162 pi over 5 once you get everything with a common denominator and all that jazz. So a little bit of math magic there to finish it out, but it's really just fraction work. So there we go. All right, and once again, the hardest part really is just getting to the integral. And then, yes, although the integral takes some algebra and you have to work with fractions, that's really, it's kind of downhill after you get to the integral.